begin. All right, so we're going to go ahead and get started here. So happy Halloween, if I didn't say that to you individually before. We are going to go over some homework. We're going to do some forces stuff, and we got some homework for Thursday. Yesterday, we did some review. I spent some time, a chunk of time, last night and today, like right before third period ended, putting grades in. So for almost all of you, your grade should now be actually up to date, okay? There are a few of you that like took a quiz late, and so it's in a different pile, and so it didn't get there. And so I will work on that today, and I will hopefully get that done by the end of the day today. But everything should be up to date, including all of the projectile motion quizzes and things. So I just want to make sure that you know that. I apologize for it taking as long as it did. Life gets crazy, right? But know that it should be up to date. Some of you, well, many of you wrote down things yesterday when we were doing review, and so you're ready to take that re-quiz. I do have that now, and I have re-quiz stuff for everything available. So if you want to do any sort of retake over any piece, any of those standards, we can do that. But again, and I know you filled that out on, was that Monday that we did that? I know you filled that out, but please talk to me so that we can make sure that we're moving toward that, okay? If you feel like you need some one-on-one, like talk to me, Ms. Cartling, I need some help. I am so all about that. I just need you to communicate that to me, okay? Let's find a time. Let's get you there, okay? I want to make sure that you end the trimester strong, because that grade does actually sit in like your permanent grade record. So I just want to put that out there. So if you have any specific questions about that or about any piece of that, let me know. Okay. Or if you feel like there's something that I have done wrong or not quite put everything in right, please talk to me. I'd rather know and get it taken care of than to have some sort of crankiness, bitterness, whatever there is. Okay. Woo. All right. Any issues or questions about that right now? All right. Okay, we are going to start by going over some homework. So it's page 146, 2, 7, 8, and 9. Why don't you go get a textbook so that we're all looking at the same stuff? We don't have to go over every single problem all the way, but let's just figure it out here. Let's figure out what we need to do. All right. Now, let's be kind. Kindness is our bond, right? That's what our goal is here. All right. Oh, I got that. All right, let's take a look here. So, questions 2, 7, 8, and 9. Of those, which ones would you like to go over? Maybe none of them. Maybe you got them all figured out. I don't know. The requests. 7, 8, and 9 were all like draw Freebody diagram things. Any of those that you would like to talk about? Hopefully, as we're moving forward, you're taking responsibility and doing your homework. So I hope the silence is, yeah, I got it, no problem. Reminder that we will have an assessment or two over this before the end of the trimester. So this is still stuff we need to make sure we're doing. Are we good? Do you need to go over anything? Or are we happy?
Can we do number 9?
For sure we can. Yeah. All right. Question number 9. Let's take a look. Draw a Freebody diagram representing each of the following objects. Sure. All right. A ball falling in the presence of air resistance. So let's draw ourselves a ball. Okay. What forces are acting on the ball as it's falling? Gravity. But we're going to call that, we're going to label that, and this is really why I wanted to do this. So thank you for asking a specific question. Those arrows have to be labeled very specifically. It's the force of the what on the ball? The earth. And then you can put in parentheses that it's FG, but you have to have it labeled the force of the earth on the ball. If, I don't know, like on a quiz, I'm asking you to draw a free body diagram and you just write FG, I will count it wrong. Okay, so fair warning. Has to say force of earth on ball. It's in the recording. Everybody knows it. Can't tell me I didn't tell you that because I did. Anything else acting on the ball? So you have a ball, or a frog in my case, falling. The earth is pulling down on it. Yeah.
Well, I don't know. It's like air resistance. Would that be normal force?
Super good question. So the normal force, because we started talking about normal force a couple days ago, right? Normal force is the force of a surface. It's always got to be a surface pushing up. So, and which way is the air resistance pulling or pushing on the ball or the frog?
Pushes up.
It pushes up, right? So it's not a surface, but we can just label it literally the force of the air on the ball. Okay? And I would just leave it like that. In terms of what we're doing, you don't have to have it labeled as another type of force, like an FG or an FN or something like that. So I would just leave it as the force of the air on the ball. Okay? And I would leave it just boom like that. Question for you. Which one is pulling or pushing harder? The earth or the air? Earth. What's your evidence? It's falling down, right? Yeah, so if this is a tug of war, the earth wins. That means that when I draw my free body diagram, and I think maybe I mentioned this, but I'm going to be more explicit right now, the length of the arrow for the earth needs to be longer than the length of the arrow for the air, okay? To show that the earth wins, that the earth is going to pull down harder than the air is pulling up. That's what I would call it. That would be a beautiful free body diagram in the presence of air resistance of a ball falling. The next one says, a helicopter lifting off of a landing pad. So we get to draw a helicopter. Everybody loves helicopters, right? Okay, there's my helicopter. Tell me the forces acting on the helicopter as it's lifting off of the launch pad. What's that? So the normal force, if it's still sitting on the launch pad, right? So we get to make a decision in here, right? So it says lifting off of the launch pad. So do we want it to be still touching the ground or no? We could do it either way. Should we take a vote? Who wants it to be still touching the ground? See a couple hands. You want to be off the ground already? It's a lot of hands. We'll do both because I don't want to, make you sad. We'll do the not on the ground one yet. If we draw here's the launch pad, and it's off the ground, what forces are acting on the helicopter? The earth? Earth pulls which way? Down. Force of the earth on the helicopter. We can put that as FG. Okay. What else is pulling or pushing? What else is pulling or pushing?
Force of the helicopter?
Yeah, there's like something. So we can't really say the force of the helicopter on the helicopter, right? Like that doesn't make sense. Like I'm pushing on myself, right? Like that doesn't make sense. But you could say like the force of the blades or of the motor. I think that those would both be okay because they're really acting on the helicopter itself. Yeah. So we can call that. What are those called? The
propellers.
Rotors, propellers, something like that. Yeah, that seems like a reasonable thing. Hey, I have a question. How is the length of my propeller force going to compare to the length of my earth force? Bigger Y?
It is going off, right?
That's what it says. That's what you guys told me. It says it's lifting off of the landing pad. Because it's going up, right? So it's moving in the upward direction. That means that the propellers are winning over gravity. Yeah, so we're going to say that we've got an upward force, and that one's got to be bigger. So the force of the propellers on the helicopter. And I'm not going to name that anything. I'm just going to leave it there. You could call it like an applied force if you wanted to. Yeah, but it's got to be a bigger force. Okay. Now, if it was still sitting on the ground just barely, so I'm going to move my ground so it's just here. What else do I need to have then? A normal force? Which way does the normal force pull or push? Which way would it go? Oh, yeah. Yeah, it would just be another force that's pushing up. The force of the, what do we call that? The surface, the landing pad, the force of the pad on the helicopter. Fn. Yep. Yep. And so now you'd add these two guys together. Boop, boop, and it has to add. Yeah. Be bigger than that. There was one more, an athlete running along a horizontal track. Shall we draw that one as well? Because why not? You know, if we're here, might as well. So let me draw my track. This is when my art skills come in handy. There I am. It's an athlete, a box-looking athlete running along a horizontal track. Tell me about the forces acting on the athlete. The earth is? Which way does the earth pull or push? Down towards the center of the earth. I'm only going to ask you that about 500 more times. So get used to saying it. Just do it. Force of the earth on the athlete. FG. What else you got? If it's just the force of the earth, then the athlete's going to fall down. It's going to accelerate downward. Yeah. What you got, Emma?
Oh, wow. First we have the normal force of the ground.
The normal force of the ground, and which way is that one pulling or pushing? It's true. It's going up. Oops, let me get a new color. Awesome. What else you got? Is there anything else pulling or pushing? If the athlete's just standing there.
Actually, the athlete's going direction.
What's that?
He's running.
He is running. Or she. I guess it doesn't say. Yeah. Which way is he or she going? We don't know. That way, because I got some lines over there, right? So tell me about some more forces. Air resistance? Yeah, so you could really take air resistance into account on all of these. I'm going to let you know, because we're lazy, we're going to assume there's no air resistance unless it says otherwise. Does that sound okay? So let's take the air resistance out of that. We totally could. We could have the air resistance going this way for sure, but I'm lazy, so let's not. What else you got? I don't know. We've never talked about this. This is good because we get to introduce some new concepts.
Would you have a horizontal force because the athlete's moving instead of going up or down? But I don't know why it would be pushing off again.
Sure. So we got to think about that, right? Have you ever tried walking?
Yep.
Yes. Have you ever tried walking on an ice skating rink or on a parking lot right after it's frozen, thawed, and then frozen again? How does that go for you usually? A little less well, right? Yeah. What is it that we're missing in that case? Friction. We haven't talked about friction yet, but we're going to introduce it right now, right? So the reason that you actually can move forward, this is weird because we don't think about this very much. And you guys were making the comment before the bell rang, but we're doing physics. Yes, you're doing physics all the time, right? You're standing here, physics is happening, right? So yes, we're doing physics all the time. Literally, when I walk, my legs are pushing on me, right? My legs are pushing, but my legs can push. And if I'm standing on ice, am I going to go anywhere? Probably just down. So there's got to be friction. Have you guys heard of friction before? Has everybody heard of that before? There's got to be friction that's causing my feet to be able to stick so that I can actually move myself forward. Yeah. So we got to add that in here because if any of you are runners, any of you are track people, you know that friction really matters, right? That's why you wear cleats when you run on like an asphalt track so that you can get more like grip so you can push harder. Does that make sense? That's why when you're playing soccer, you have more grip so you can move faster, so you can do it. Like literally that's what happens. So you've got friction that goes this way, and we'll talk about what that is in just a minute. So the force of the surface on the athlete, that's a frictional force. It pushes the other way. That's weird. But without it, you can't go anywhere. And then you've also got your leg muscles, right, that are applying a force to make your body move forward as well. So we've got a force this way. Oops. Force of your, we'll just say legs. Leg on. Yeah, what's up? Yep. How we doing?
In a vacuum, there's no friction or air resistance, right?
In a vacuum, there can be friction for sure, but there isn't any air resistance because there's no air.
Okay.
Yeah. So vacuum equals no air means that physics is easier. How are we doing? Okay-ish? Okay. We're going to come back to friction later, I think maybe even today, but right now what I want to make sure that we're feeling good about is normal force. Did we write normal force down? Hey, we did. Awesome. On our force inventory. I couldn't remember for sure. So I just want to remind ourselves of this because we're going to do some problems with this today. Normal force is the force of the surface acting on a force. I'm just getting this back in my head and helping you to do this too. This was on was this a orange sheet or something that you guys were writing on? Yeah. It acts perpendicular to the surface. It's determined based on other forces acting, and that's what we're going to do today. We're going to do some math to figure that out. It doesn't cause acceleration really, but kind of it does. And that's what the picture looked like. All right. Did we say a word that starts with E last time? We did. Yeah. This fun word, equilibrium. What does equilibrium mean? Yeah. The forces that are acting are all equal to each other so that the total force, if you add them up all together, they have to add up to 0. Yeah. All right. We've got all of the information we need to do some problems. So here we go. Hey, look. This is our first opportunity to plug in some numbers to all of this business. So you will need a calculator today. So if you don't have one out yet, why don't you get one out? Okay. And I think that for now, that's all you're going to need. We might throw in some more things in here in just a minute as well. But for right now, let's just do that. We start with easy stuff, right? Easy stuff that we can conceptualize. Like a frog sitting on a chair. Oh, he's back. This is actually asking us to actually now find some numbers to determine the normal force acting on a frog while he's sitting on a horizontal surface. So you remember back to the very beginning of our time together, this was so long ago now, I told you that whenever we do a problem, we're going to do this guess method, right? Where we're going to start out with our givens. And part of our givens when we were doing the projectile motion problems was we need to draw a picture. And we're going to keep doing that. But the picture we draw now is going to be a very specific picture. The picture we draw is our free body diagram, FBD, free body diagram. Okay? So for this problem and for all of the problems we do with forces, we're going to start with a free body diagram. We've done it already, but I want to make sure that it's in your head because you're going to get to do a lot of them. Determine the normal force acting on the frog while he's sitting on a surface. So let's draw ourselves a surface. Let's draw ourselves a frog. And this is another one of those funny things. As long as you take it step by step, friends, these problems are easy. If you don't, they make it really hard. So step 1 is always to draw a free body diagram. What forces are acting on my frog? Earth. Which way does the earth pull or push?
Down.
Indeed. I'm going to mark that FG because I know that's the gravitational force. Any other forces acting on my frog as he's sitting on the chair there? Normal force, but it's really the force of the
Chair.
Indeed. FG or FN is what I'm going to mark with that one. I'm going to add those two together. Okay, so there's my free body diagram. The question, the problem is asking us to determine the normal force. So we want to know the number that this equals. If we look at our handy dandy orange sheet, there is not an equation for finding the normal force. So that means we need something else. And the thing that we need is called an F-net equation. Have we talked about F-net equations yet? I can't remember. We maybe like wrote one out kind of. Oh, we just said that F-net had to be something. So I wrote down F-net, but we haven't actually done one. So let's write down. So here we go. This is your opportunity. We're going to remember this forever because we get to do this on Halloween. Halloween is our day to write F-net equations. Happy Halloween, friends. F-net. F-net literally means just write down the forces. So if you've drawn a good free body diagram, life is good. Because you're just going to write down all the forces acting. Can you do it? Sure. FG plus FN. Hey, that's an F-net equation. How are those forces going to compare? What are they going to add up to? Why?
If the chemical magnet stay on the surface, if the frog's not going to equilibrium.
Because he's in equilibrium? Because the forces have to be the same. Because he's not going anywhere. He's not accelerating. He's not moving. Yeah, so they've got to add up to 0. One of them's got to be negative. Malik, which one do you want to be negative?
Gravity.
Gravity. How come?
Because gravity pulls down.
Seems reasonable. I think that's all right. Let's call it negative. That's nice. So now we know that FG and FN have to be equal in magnitude, right? So if I was going to solve for FN, because that's what it says, determine the normal force, I'm going to say FN, I'm going to add FG to both sides. Do you see how I'm going to do that? Because right now it's subtracting FG, so I'm going to add FG to both sides. And hot diggity, look at this. FN equals FG. Well, great. Do I know FG? I can figure it out, can't I? Because we do. I'm going to bounce over here to my force inventory for just a second. That's that orange sheet that you have in front of you. I can calculate FG because I have it right there. It's going to be the mass of my object times 9.8. The negative here just means that same negative. So when I plug it in, I'm just going to use 9.8 because I already took care of my negative sign. So I'm just going to calculate here my FG. I'm going to say, oh yeah, FG is mass times the acceleration due to gravity. That's 0.45 kilograms times 9.8 meters per second squared. Josie's like, I've got a calculator. I can do that right now. Ben says, hey, I've got a calculator too. I can do that too. Not that I don't trust Josie, but sometimes people make mistakes. And we just want to make sure that everybody's calculating it so you know how to do it, and so that when you're doing it on a homework problem or a quiz coming up or something like that, you got it. Josie, did you get an answer?
Yeah.
What'd you get?
4.41.
Say it loud.
4.41.
4.41, she says. What's?
Is that going to be positive?
So the question is it positive or negative? Really, I'm just talking about the magnitude right now.
Okay.
Does that make sense? And so I'm just going to leave that as positive because I already took my negative into account.
All right.
The one kind of, I don't want to say it's a trick, but the one thing you have to pay attention to is that you don't want to put your negative in more than once. Because if you do, then things get messy. It's also kind of a nice logical thing here because you know that FN has to be positive. So if you end up with a negative FN, you know something happened that was wrong. Does that make sense? Okay. Ben, do you agree with that 4.41?
Yes.
Awesome. Okay, cool. 2 people agree. Anybody want to disagree with it?
I got to see you.
Were you just trying to pick a fight there? Was that what's happening there? Okay.
Excuse me.
What are the units for a force? Have we calculated any forces yet? This is the first time. First time for F-net equations and first time for calculating a force today. It's a great day. Oh my gosh. Just a note that a kilogram, that's a kilogram, times a meter per second squared, that's your acceleration. You could write this if you wanted to, if you had lots of extra graphite and you just wanted to write things down. You could write this as 4.41 kilogram meters per second squared. You could. I wouldn't count it wrong because it's correct. But I'm not saying y'all are lazy. I'm saying I'm lazy. Instead of doing that, even though I strongly dislike the man, I'm going to go ahead and write just an N for Newton. Okay? I'm going to go ahead and write an N for Newton because a Newton is a kilogram meter per second squared, and that is much easier, much less to write.
Why do you not like that? Yeah.
Oh, I'll tell you. Not right now. Give me, I think tomorrow will be the day. Yeah, something to look forward to. Yeah, got to pace ourselves here. So Fn is equal to 4.41 newtons. How'd we do? We okay? Okay. All right. The next problem gets a little bit harder. Are you okay with that? Not really? You're up for a little challenge. It's a beautiful Halloween day. You're up for a little challenge. Here it comes. Oh, I forgot to get my little... Oh, we'll use this. Okay. This will work. I'm going to take my frog for a walk. We got a little leash on him. He likes to go on a walk. I used to have like a string that was really like the perfect size so that I could really take him on a walk and he liked it. But I don't have that anymore, so you're just going to have to imagine. What? Do you do this? Do you take your frog on a walk too?
Yeah.
It's good. It's good for them to get over there.
Do. It's
Yeah,
fun.
yeah. What?
I definitely do.
Yeah. All right. So instead of the frog just sitting around all day, we got to get exercise. So I'm going to take the froggy for a walk. So here he is. Okay. Now the question says.
I'm sorry.
No, I'm just laughing at you because that's what I do. So here he goes. He's going to go for a walk. Yay! Now as he goes for a walk, right? He's so happy. He loves going for a walk. As he goes for a walk, I'm pulling. Okay. I'm pulling a little bit up and a little bit over. Vectors. I'm pulling a little up and a little bit over. But here's the funny part of this, you guys. Because I'm pulling a little bit up, does that change the force of the earth acting?
Yeah.
Does it change the force of the earth acting?
Wait, no.
No. But does it change the normal force pushing up? It does. Did I give you the example from a while ago? I can't remember if it was in this class or the other class where we were carrying plates up doing the dishwasher. Did we do this example or no?
Yeah.
Yeah, when we were back at the back, right? Who got to hold those? Yeah. Oh, man. Yeah, you got to hold them, right? Yeah. And so the whole deal, right, was that you had your arms only pushed up as much as they needed to, right? And the earth does the same thing. The earth only pushes up as much as it needs to keep the frog from accelerating down or, not push him up. Okay? So the funny part of this is, ladies and gentlemen, that the normal force changes. The normal force changes. There's not one right answer for what it's going to be forever. In the first problem, when the frog is just sitting watching TV, the normal force is 4.41. Let's draw a picture for question 2. So we're going to draw a Freebody diagram. So I'm going to draw this is the street that I'm walking my frog on. I'm going to go ahead and draw the frog. What forces are acting on my little frog? The earth, right? Kind of like with the projectile motion problem, they're always those like the easy ones. So you just got to say them out loud fast. The earth is pulling straight down, I'm assuming, yeah? FG. What else is acting on my frog? What's that? Yeah. So I'm hearing two different things. So Stella, you said the normal force, and Josie, you said were you talking about the normal force or were you talking about a different force? Which force were you talking about? The force of the what? The applied force or the force of the leash or something? There's a lot going on in this problem. It's true, but we can handle it. We're smart kids. Okay? So we got the force of the surface on the frog. going to call that Fn. And then we've got the leash, right? The leash that Josie was just talking about. Now, this is a little bit funny, but I know you guys can do this. You'll also see why we spent so much time with those vectors before. Because they're back. Oh, yeah. 65 degrees relative to the horizontal. So it's going up something like this. There's 65 degrees relative to the horizontal. This is the force of the leash or the rope on the frog. We'll call that an applied force.
Now,
Yeah.
what's the 2.5 newtons?
Mm-hmm.
Is it like on the left side of the frog being pushing it, or is it
It's
on
the green one.
leash? So it's on the green leash.
It's the green arrow. Mm-hmm.
Okay.
Yeah. Which means that we have to do what to it? We have to break it into pieces. Why? Because the only part of it, so this is a good question I'm gonna ask, or I'm gonna say this to everybody. So Isaac was just saying, so this 2.5 that's pulling up like this, that's all well and good, but do you notice that it's going up at an angle?
Yeah.
So as I'm taking my frog on a walk, where is he going?
It should be on the ground.
Does he just sit still on the ground though?
No, it should be going forward.
He moves, doesn't he? For sure he does. He moves along the ground, which means that he's got some force that's pushing him this way.
Yeah.
Right? Some force that's pushing him horizontally. And some part of that force that's pushing up. Are you with me there? Does that make sense? So some of it's going over, some of it's going up.
Sine and cosine.
We got this. This is why we did vectors last unit. Right? We can do it. I know you can. And friends, if you don't know how to do it yet, statement number 1, you don't say, oh, I can't do it. That is not right, okay? That is not true. I know you can. Sometimes it just takes a little while to learn it, but I'm here for you. We got this. So we're going to have part of it that goes this way. Work with me here. This is going to be the applied force in the x direction. Is that okay? And then we've got the applied force in the y direction. Absolutely a little more tough. Absolutely you can do it. I believe in you. I know you can. Okay? It may take a little practice, but that's why we're here. It's to practice, right? We got this. All right. Can we figure out what FAY is? That is the opposite side. And I know the adjacent side, or excuse me, the hypotenuse, don't I? Okay. So I've got opposite and I've got hypotenuse. So that's going to be sine, cosine, or tangent. Do you guys believe him? He gets loud sometimes, but sometimes I don't trust him completely. So I want to make sure. You guys okay with that? Yeah, sine. The sine of theta is equal to the opposite over the hypotenuse, yes? So the sine of 65 is equal to FAY over FA, which is 2.5. So you can say that FAY is equal to 2.5 sine 65. How we doing? Did I write it down wrong? Are we okay? 2.5 sine 65. I think that's all right. Okay. We're going to plug it in. What do we get for a number? 2.27. That's my FAY. That's this one here. What was FG? Do you remember what FG was? I'm going to do it again because I don't remember. FG is equal to M times A sub G. The mass is the same as it was. We did this already. I'm just writing it down again in case you were confused before. 0.45 kilograms times 9.8 meters per second squared. What was that, 4.41? And friends, all I care about, I want to know N. So now it's kind of like you've got two people pulling on one side of the tug of war rope, one person pulling on the other side. But is the frog going up or down? And if the frog isn't going up or down, then what does that mean about these two forces as compared to this one? It's in equilibrium. So all three of these have to add up to 0.
Wait, the Fn plus Fay equals Fg?
Yeah.
Or is it just Fn equals Fg and Fay?
So let's not overthink it. Okay? Because you're going to get yourself into these funny little loops and you're going to second guess yourself and be like, I don't know. So you know what we're going to do? I'm going to look back up here. It says, write an F-net equation. You say, sure thing, because F-net equations are going to point you in the right direction. So here we go. We're going to write an F-net equation. This is the best part. Here it comes. F-net. And hey, by the way, I'm only looking in the Y direction, right? He's going to move in the X. I don't care about that yet. So all I care about is the Y direction. So I'm going to do F net Y. All I'm going to do is look at the forces that are acting in the Y direction. That's the up and down direction. I'm going to highlight them in my picture because it's nice to be able to see them. Here's one. Here's one. Here's one. Yeah? So let's put them together. Let's write them down. I've got the force of the earth, that's Fg. I've got the force normal, that's the force of the surface. And I've got the applied force, Fa. Oops, I was going to do the purple one though, sorry. Oops. In the Y direction. How are we doing? Are we okay here so far? All three of those forces have to add up to 0 because it's in equilibrium. Malik's going to say, Miss Carbling, some of these forces are in the negative direction. I'm going to say, you're right, Malik, they are. And which ones are you going to tell me I need to make negative? Gravity. Because it's going down. The other two are going up, so we're going to call those ones positive. Right? Sweet. This is really good stuff to write down, you guys, so that you can do this later. You can watch it again, or you can process it again. Write it down with me. There you go. All right. So now we just need to get Fn by itself. Are we okay so far? Yeah? Here we go. I'm going to move. Actually, no, here, we'll just do it this way. Then I've got more space. All right. I want Fn all by itself. So I can either move Fn or I can move everything else. I'm going to move everything else. Is that okay? When I move everything else, Fg is going to become positive, right? Because I'm going to add Fg to both sides. Yes, no? Yes? I'm going to move Fay, and it's positive right now, so it's going to become negative. Let me write it out so that it makes sense. Here I go. So I'm going to add Fg to both sides. And I'm going to subtract Fay from both sides. And so then I've got Fn is equal to, here it comes, Fg minus Fay. And that right there tells you exactly what you want to do. So you've got Fg, it's 4.41. You've got Fay, it's 2.27. You're going to subtract them, and whatever's left is going to be your normal force. How we doing? So?
So compared to the last one, our Fn is not, Fn by itself is not equal to Fg.
Correct.
Okay.
That is not a trivial statement that you just made.
It's going to be a little bit less than our Fay. So that it just, when you add them, they balance out to make the balance.
You got it. You got it. How are we doing, team? Are we okay? Yeah? All right. So let's write this down. Let's write it out here. Now you get your calculators out. You're going to say 4.41 minus 2.27 gives you how much for Fn? What is it? 2.14? The normal force is much less, isn't it? It's much less. Is that feeling okay? Yeah. Okay. Cool. I'm trying to say what I'm going to do next. Hold on. Let me see where we're at. Cool. I want to. Do you want to do one more like this?
Yeah, let's see it.
Let's do one more like this. Okay, I don't have one that's written, but I'm gonna write it. We're gonna make one up. Let's go grocery shopping.
Yeah.
Shall we? Let's go grocery shopping. So you've got a grocery cart that has a total mass of 10.3 kilograms. Okay. And you are going to push on that cart. Now, when you go grocery shopping, unless you're less than 5 feet tall, then you're generally pushing down on the grocery cart. Are you with me there? Yeah? So we're going to push down on the grocery cart, which means that I'm just letting you know that this is what I understand, that some of the force that you're pushing is going to get the cart to move. But some of that is going to push down. Are you with me there? Right? So those of us that are short, when we push it, like all of our force goes into moving that grocery cart. Much more efficient than those of you that are tall, and a lot of that force goes into pushing down. Are you with me there? So it's changing the normal force. So one of those advantages of being short. So here we go. Grocery cart of mass, blah, 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 blah. And we're going to push with a force of, let's say, 5.2 newtons at an angle of, 15 degrees below the horizontal. So we're pushing down, right? You get that? We're not, because nobody's gonna push up on a cart. Like maybe my 2-year-old, right? When she's like, I want to push the cart, Mom, right? And she's like standing here like this, like that, right? So like she's kind of pushing up and out, but nobody else does that. Okay. Only the 2-year-olds that are going grocery shopping are doing that. Everybody else is pushing down on the cart a little bit. All right. So pushing below the horizontal, I want to find the normal force on the cart. Think you can do it? Give it a try. Everybody needs to do it. I want you to have it on a piece of paper right now. So you're going to draw what to start?
The diagram, the
Freebody diagram, right? Of a shopping cart. That is a pretty good shopping cart, not gonna lie. I'm pretty proud of myself. Yeah. How many forces do you have acting? 3. I'm gonna help you out with the applied forces because it's kind of a funny one. So it's gonna be down like this. Okay. The force of the person on the cart. The angle there is 15 degrees. I'm going to let you just chew on that for a couple minutes. Let's see how we do.